All right, welcome to this explainer. I am absolutely thrilled to have you here today. Look, if you've been using ChatGPT, Claude, or really any of the AI assistants that have basically taken over the world lately, you've probably caught yourself wondering at some point, how exactly are these things working? How does a computer program suddenly seem to understand us so incredibly well? Well, today we are going to completely demystify the magic behind large language models, or LLMs. And don't worry, we're going to do this without getting bogged down in mind-numbing math. We are simply going to look under the hood together, breaking down exactly how these fascinating systems actually operate. Here's a quick roadmap for today. We'll be hitting the ultimate autocomplete, how AI reads using tokens, the transformer engine, pre-training, fine-tuning, and finally, the magic and the limits of this tech. Okay, let's dive right into section 1, the ultimate autocomplete. Before we get into the nuts and bolts, we really need to reframe how we think about what an LLM actually is. I mean, it's incredibly tempting to imagine there's this little robotic brain in there, thinking and pondering exactly like we do. But actually, scratch that, it's not quite right. At its core, an LLM is basically an insanely powerful pattern spotting system. Just imagine someone who sat down and literally read every single book in the British Library, plus every newspaper article and millions of online conversations. After consuming all of that, they developed this incredible, almost superhuman knack for predicting what word should logically come next in any given sentence. And that is essentially what an LLM is doing. It analyzes billions of text examples to identify human language patterns, how we structure sentences, connect ideas, all of it. When you ask it a question, it's not looking up the answer in some giant database. It simply generates a response one predicted word at a time based on all the patterns it absorbed. It is, for sure, the ultimate autocomplete. Moving right along to section 2, how AI reads tokens. So if it's really just predicting the next word based on patterns, how does it process the words we type into it? I want you to stop and think about this for a second. How does an AI actually read your prompt? When you type, "Hello, write me a poem," it totally feels like you're sending sentences to the model. But under the hood, the AI does not see text the way we do. It doesn't see letters or words, because computers fundamentally only understand numbers. To bridge that massive gap between a raw text and mathematical computation, the model uses a process called tokenization. Tokenization basically chops your text up into tiny, bite-sized units called tokens. Each of these tokens is then assigned a very specific integer ID. So to a machine, the word learning isn't a word at all. It might just be the number 4085. The AI reads math, not letters. Now, what's really interesting here is that you might assume an AI just splits text space by space, word by word. But modern byte pair encoding, or BPE, is way smarter than that. It takes a complex word like programming and actually splits it into two tokens, program and Ming. This is absolutely brilliant because it helps the model understand that programming, programmer, and programs all share the same root. And get this, it's smart enough to keep things like a snake emoji completely intact as a single token. Once we have all these numerical tokens, they get turned into what we call word vectors. You can think of a word vector as a set of high-dimensional GPS coordinates for meaning. By analyzing millions of documents, the AI learns to plot these tokens on an imaginary, mathematical map. Words with similar meanings end up placed very close together. So cat is placed right near kitten, and dog. And because it is all mapped out mathematically, the model can literally do math with meanings. The spatial relationship between Paris and France is the exact same distance and direction as the relationship between Berlin and Germany. It's mind-blowing, but this mathematical map is exactly how the model begins to sort of understand context. All right, let's look at section 3, the transformer engine. Now that we know how the AI turns our words into math and maps their meaning, let's talk about the engine that actually processes all of this data. This is the architecture that allows the AI to read, remember, and generate text. It's called the transformer. It was introduced back in 2017, and it absolutely changed the world. While it sounds incredibly complex, we can break this daunting architecture down into 2 digestible steps that happen in sequence. Step 1 is the attention step, where words literally look around the sentence for context. And step 2 is the feed-forward step, which does the heavy lifting of actually predicting the next word based on the context it just gathered. Let's zoom in on that first step for a second. Attention mechanisms act exactly like a matchmaking service for words. You know, human language is incredibly full of ambiguity. If I use the word bank, do I mean a financial institution or the muddy edge of a river? Well, the attention mechanism allows the token for bank to look at all the other tokens in your prompt. If it sees the tokens for money, deposit, and cash hanging out nearby, it instantly shares that information, modifying its own mathematical vector to lock in the financial meaning. This stage allows words to pull together all the context they need so the feed-forward network can make a really smart prediction for the next word. Which brings us to section 4, pre-training, or absorbing the internet. So we have our tokens and we have our transformer engine, but an empty engine doesn't know anything, right? We have to build the AI's brain. And that starts with pre-training. 14.8 trillion. I really want you to just let that number sink in for a second. That is the sheer scale of tokens used to pre-train one of the recent frontier models, DeepSeek v3. During this phase, researchers feed the model gigantic slices of the internet: books, articles, websites, code repositories, the whole shebang. The model just reads text, hides the next word from itself, tries to guess it, and corrects its internal math if it gets it wrong. Doing this across 14.8 trillion tokens takes thousands of highly advanced GPUs running for months, and it easily costs millions upon millions of dollars. But here is the catch. Pre-training just builds a base model. Because it's read the whole internet, this base model has unbelievable capability. It knows grammar, facts, it knows how to write Python code, but it has absolutely zero idea how to behave in a normal conversation. Think of it kind of like the first 18 years of a human's life. The AI has absorbed the world's knowledge, but it lacks basic manners. If you ask a raw base model a question, instead of answering it, it might literally just generate 3 more related questions. Why? Because out on the wild internet, questions are very often followed by more questions. And that leads us perfectly into section 5, fine-tuning, or teaching behavior. This is the stage where that raw autocomplete engine is meticulously molded into the helpful assistant we all know and love. And this brilliantly illustrates the difference between our two stages. Pre-training builds the raw capability, costs millions, and burns through trillions of tokens. But fine-tuning, which is also called post-training, is relatively cheap, uses maybe just a few thousand carefully curated examples, and is entirely focused on shaping behavior. If pre-training is the first 18 years of life, fine-tuning is the targeted job orientation that teaches the model how to actually do its specific job as a chatbot. So how do they actually do it? Well, they use a few specific methods. First up is supervised fine-tuning, or SFT. Here, humans write out thousands of perfect prompt and response pairs, and the model simply learns to imitate that helpful format. But imitation isn't quite enough. We also use RLHF, reinforcement learning from human feedback. This is where humans rank multiple AI answers from best to worst, teaching the model what humans actually prefer, like having a polite tone or refusing to help with harmful requests. Finally, there's a newer method called direct preference optimization, or DPO. It does something similar but optimizes those preferences directly into the math, making the whole alignment process much more stable. This is how we inject a helpful tone and enforce specific formatting. Finally, let's wrap up with section 6, the magic and the limits. Through tokens, transformers, and all this training, we end up with incredibly capable tools. But we absolutely have to ground them in reality because they have strict limits. Because LLMs are fundamentally just predicting statistical patterns, they have flaws. The most famous, of course, is hallucinations. Because the model doesn't reference a fixed database of truth, it can easily generate facts that sound completely plausible but are just entirely false. Second is bias. Since it learns from human-generated internet data, it naturally reflects all the statistical quirks, cultural patterns, and inequities found in that raw text. And finally, there's catastrophic forgetting. If you push a model way too hard during fine-tuning to learn a highly specific task, it can actually forget the broad general skills it learned during its multi-million-dollar pre-training phase. So, rule of thumb, you always have to fact-check the output. But even with those limits, the capabilities we're seeing are staggering, and it's sparked a really fierce debate among researchers. Take Stanford psychologist Mikhail Kosinski, for example. He's commented on how modern models can easily pass theory of mind tests, which measure the ability to understand others' mental states. He suggests this ability emerged spontaneously as a byproduct of increasing language ability. But this idea of spontaneous reasoning is highly debated. Other prominent researchers, like Emily Bender, argue the exact opposite, saying that these models are really just stochastic parrots, mindlessly repeating complex statistical word sequences without a single shred of true understanding. And that is exactly where I want to leave you today. You now know the entire pipeline, from how text is smashed into numerical tokens to how the transformers' attention mechanisms find context, to the massive cost of pre-training and the behavioral shaping of fine-tuning. But the ultimate philosophical question still remains completely unanswered. As these models scale up and become eerily, almost frighteningly good at mimicking human thought, is it really just a stochastic parrot predicting the next token? Or is there a spark of real reasoning spontaneously hiding in all that math? Thank you so much for joining me on this explainer today. Keep asking questions, keep learning, and I'll catch you next time.